In this video, we're going to see if we can derive the minimum sampling frequency that's necessary to capture a particular signal properly. So just to remind you, the basic idea is that we're going to take a continuous time signal and we're going to attempt to sample it. And the idea is that we want to use just enough samples so that we can accurately reconstruct the red signal from the blue samples. We don't want to overdo the number of samples because then we just have that many more samples to have to carry around with us. But we don't want to underdo it either because then we won't be able to accurately reconstruct the red signal. And all I'd like to point out first is that intuitively speaking, the number of blue samples that you need is going to have a lot to do with what the frequency of the red signal is. So for example, if I introduce a high frequency bump to the red signal, then you can see that my blue samples aren't going to be sufficient. Because I've added a higher frequency event to the continuous time signal that I'm trying to capture, in order to capture that, I'm going to need to use more samples. So for example, if I double my sampling frequency now, I will have a much better chance of being able to identify that peak. So generally speaking, as you increase the frequency of the signal that you're trying to sample, you'll have to increase the sampling frequency. Those two go hand in hand. So let's see if we can work through that mathematically. The easiest way I know to do that is to look at a demonstration. What you're looking at here is a 10 Hertz cosine. That's the thick blue line. And then you're looking at samples of that. So the samples are the green dots. And from those green dots, what I'm doing is I'm attempting to reconstruct a cosine. So in other words, if I just gave you the green samples and I said, please try to rebuild the cosine that those samples came from, that's what would be the orange curve. So the blue is the original and the orange is the reconstructed signal. And as long as the blue and the orange are the same, that means that I had enough samples. So I can reduce the sampling rate and I can see whether or not the samples that I get from that reduced sampling rate are still enough to rebuild my cosine. And again, as long as the original and the reconstructed signal are the same, then I did have enough samples. So right now it's a 10 Hertz cosine. I'm sampling it at 50 Hertz. So that would suggest that I get 5 samples per period, and that's exactly what I have. I have 1, 2, 3, 4, 5 samples, and then we start the next period, 1, 2, 3, 4, 5 samples for that period. So it's 5 samples per period. And that would imply that my discrete time frequency is 2 pi over 5, and that's where the 0.4 pi comes from. So this is definitely enough points. So what I'm going to do now is I'm going to start reducing the sampling frequency. I'm going to essentially ask myself the question, can I get away with fewer points? So here, now I've got myself down to 40 Hertz. Okay, 40 Hertz for my sampling frequency implies 4 samples per period. So a moment ago I was at 5 samples per period, now I'm at 4 samples per period, and it seems that that's still enough for me to rebuild my cosine. So 4 samples per period is still enough. Now my discrete time frequency has increased to half pi. So that's good. Let's keep reducing the sampling frequency. So now I'm sampling at 30 Hertz. That implies 3 samples per period. So I've gone from 5 all the way down to 3 samples per period. But mathematically, that appears to still be enough to rebuild my signal from. The discrete time frequency has now gone up to 2 pi over 3, 2/3 pi. So that's good. Let's keep decreasing the sampling frequency. Now I'm down to 2 samples per period. Okay, I'm sampling at 20 Hertz, and at 2 samples per period, I'm still able to reconstruct my cosine. There's still enough points there. Okay, my sampling frequency is now pi radians per sample. So I decrease the sampling frequency a little more, and all of a sudden things change. So now I've decreased my sampling frequency to 19 Hertz. I'm getting slightly less than 1 sample per period. And all of a sudden, if I take those samples and I try to fit a cosine to them, I no longer get my original signal back. Okay, what I wind up getting back is a signal at some lower frequency. And decreasing the sampling frequency beyond that doesn't make things any better. In fact, if I sample it at 10 Hertz, if I do 1 sample per cycle and I try to rebuild my signal based on that, you can see I get the comically incorrect reconstructed signal which is a DC, okay, which doesn't oscillate at all, and that's definitely not right. So it looks that, like, by power of observation, the bare minimum I need is 2 samples per period. Okay, as long as I have 2 samples per period, that looks like it's enough. And 2 samples per period corresponds to 1 pi radians per sample. So let's write that out. So we need a minimum of 2 samples per period. As long as I get 2 samples per period, I will be able to rebuild my cosine. So really what I want to say is that t has to be at least, it has to be greater than or equal to 2 samples per period. And if t has to be at least 2 samples per period, well then omega, which is 2 pi over t, 2 pi over the period, that would imply that that number has to be less than or equal to pi radians per sample. And if we remember that omega is also equal to 2 pi f over f sub s, and we've just worked out that that has to be less than or equal to pi, then by rearranging terms I can say one of 2 things. I can either say that f has to be less than or equal to fs over 2, or equivalently I can say that fs has to be greater than or equal to 2f. And let's put a box around that. This is the famous Nyquist theorem, and it tells us how many samples per second we need to take in order to accurately capture a signal at any frequency. So for example, in the previous video, we started by working with a 30 Hertz signal. Well, according to Nyquist, in order to accurately capture that 30 Hertz signal, we must work with a sampling frequency that's at least 60 Hertz. And in our case, we were using 90 Hertz, so that's why we were able to successfully sample that signal without aliasing. On the other hand, when we were sampling the 60 Hertz signal, that implied that we should be using a sampling frequency that was at least 120 Hertz. But that's not what we were doing. We were using a sampling frequency that was 90 Hertz, and we can tell from Nyquist that if you're using a 90 Hertz sampler, the best you can do is sample up to 45 Hertz. And because our 60 Hertz signal is bigger than 45, that's why we got aliasing. So again, as a reminder, aliasing is what happens when you don't use a high enough sampling frequency. And when that occurs, what happens is that when you try to rebuild your signal, it winds up looking like a lower frequency than it was when you started. In fact, it'll wind up looking like something on the range, for example, for the 90 Hertz sampler, you're guaranteed that whenever you rebuild your cosine, you're going to get something from 0 to half of fs, in this case 45 Hertz. Okay, so because 60 doesn't fit in this range, when you go to try to rebuild the signal, it will rebuild it somewhere in that range. In the case of this particular example, it worked out that when we rebuilt the cosine, it wound up looking like a 30 Hertz signal, and that was in fact the aliasing that we were discussing in the previous video. So again, as long as you abide by the Nyquist theorem, you won't get aliasing.